So now we are going to study the approach, which takes us one step further. Basically, we are learning from the data, not making handmade rules which are not very robust. We learn directly from the data. So this is we are in that direction. So Gaussian mixture models. So what are Gaussian mixture models? Let us start with another approach called K-means clustering. So what is K-means clustering? Okay, let me start an intuitive understanding. So let me call this as K-means and GMM, today's class. Okay, so what is K-means clustering? Let us say if I give you some data here, let's say this is a two-dimensional space, and there are points here, here, like that. What can you say about this data? What can you say about this data? Anybody would like to speak out? See these, if I simply have to tell the mathematics, then you have already seen it. But now I want interactive discussions so that we actually make sure that we understand things very thoroughly, and we understand why things are made in this way.
These data are distributed in 3 clusters, we can say that.
Very good. Very good. So if you ask anybody, what do you see? He will say, or she will say, I see 3 clusters, 3 groups. But the data which is given to you is just a list that, okay, this is some x1, this is some x2. So you are just given x1 and x2 values, right? Your x1 here is, let's say this is 1, 2, 3, 4, 1, 2. Somebody will say 1, 0.5. This is 1 point, right? 1, 2, another point. Then let's say this is 1.1, comma, how much is this? 0.9 something. Oh, this is 1, sorry. Yeah, this is another point. So you are given this list. In this list, you do not see 3 clusters, but then how do you cluster this list into 3 clusters so that these 3 clusters are formed? If I assign a color here, color, and I can assign some color like red, 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 blue, 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 green, 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 and I will say this is my red cluster, this is my blue cluster, this is my green cluster. So how do you get these clusters from the data? So to do it, what will you do intuitively? What would you like to do? Means, can you think of some intuitive algorithm that you can define these clusters or you can get these clusters? Anybody?
Sir, we'll try to find centroid of each clusters.
Yeah. Okay. So what a person can do is he will say the red cluster has got a centroid here. Means basically you say I define my cluster in terms of just the centroids. And if somebody tells me these centroids, I can basically I can represent this whole data in terms of 3 centroids. That okay, I see this point with some spread, this point with some spread, this point with some spread. This is called K-means clustering, right? So the parameters for this model, how many parameters are there for this model? One, this centroid. So okay, let me write it. So one is this mu vector. One is this blue mu vector, and this is this mu vector. So total how many parameters? How many parameters?
3 parameters.
Yes?
3 parameters.
Think carefully.
6.
6, yeah, because
6.
each mu will have 2 values, x1 for x2, right? So total 2 into 3, 6 parameters. So you have represented this whole data, which was, let's say, hundreds of points, which means about 200 data points, 200 numbers in terms of these 6 numbers. So a lot of data compression has happened, right? And also this tells you more about the structure of the data, that data is organized in this fashion. So how do you now get these values of the mu? How to estimate mu? How to estimate these mu's?
Once we know which cluster a point belongs to, we can take the average of all those points.
Sample mean, we can say sample mean.
Yeah, but okay. So to estimate the mu, you need to know which points belong to this cluster. And you don't know what points belong to that cluster.
Calculate distance measure to identify
Yes.
point.
Very good. So we have of distance. Very good. Okay. So first of all, we have to have a notion of distance here. Let me write it. So what kind of distance we can use?
Log of
So we can take simple Euclidean.
Yeah, very good. Euclidean distance. Simple choice. We can use any kind of distance metric here, but Euclidean is something very easy to see. And you can use cosine similarity or anything, given that you have to modify your space in that particular way. So distance is Euclidean, which means basically x vector minus y vector, right? Where x and y are 2 points in this space. Both x comma y belong to R2, right? Now, okay. And this means, how do you choose your clusters now? Okay, means, okay, so, okay, let us first, given clusters, given this mapping, basically, given this color of cluster, basically given the cluster for each x, how to find mu? How do you find mu?
sample mean of the data values all in the cluster.
Okay, mu is equal to, yes, summation
Average.
for all xi. I is such that ci is equal to, let's say, c. Means you take all the xi which belong to this particular c, right? And then you say 1 upon total number, whatever is the number of points. So basically what I'm saying is, you have xi is this vector, right? Ci is this color. So when you say all the xi, take all those xi such that the color is equal to this particular c, right? And then total number of points, which is simply, is this mathematical notation clear?
Yes.
Okay, given an x, we can find mu. Now the reverse problem. Given mu, how to find x? Given mu c for all c, for all the colors, you know the centroids, how to find x? How to find ci for each xi?
We will compare distance from each centroid.
Yes, very good. So you will say ci, the color of the ith sample, basically you look at this point and its distance from mu of Ci, right? Am I correct? Or just put C? Sorry. Mu of C, and you take the C which maximizes this, sorry, argmin minimizes this distance. Argmin takes C such that this distance is minimized, right? You pick a C, basically you know this cross, then you know this cross. If I give you this white point, you will compare this with all the centroids. Whichever has the minimum distance, you assign it to that cluster. So since this is minimum distance, you will say this also belongs to the blue cluster. So you will say my Ci is blue. Is this clear?
Excuse me, sir.
Yes.
Sir, how we find the distance and we discriminate these three clusters separately? I'm not getting this.
Okay. So you know the centroids, that there are 3 centroids, but you do not know.
No, sir. Initially, we don't know the data are in group in a 3 cluster. Then how we clustered in three group?
Okay, good question. So I'm not asking how does everything start. I'm just saying if we somehow know mu, how do you find Ci for each xi? Right?
Okay, sir.
If you somehow you know mu, then how to find Ci for each xi? Right? And similarly, we saw if somehow you know the 3 clusters, how do you find the centroid? Okay. Now what happens is, now we will use an algorithm called EM algorithm, expectation maximization algorithm. As per that algorithm, you can see the details in the slides. I will not go through the details. So you choose any 3 random points as your centroids. So the algorithm is like that. Step 1, choose 3 random points as mu I, mu C. Choose any 3 random x as mu C for each C. Right? Basically, for choose a random xi as mu C for each C. Right? Then step 2. So basically what has happened that you had this data, you just took any 3 random things. This is green, this is red, this is blue, let's say, right? Which are wrong, right? This is not the right thing, but you just started from any 3 points, right? Now what will happen? Now do the step this, given mu C, find Ci for each xi, or you can say re-estimate.
Sir, I have a doubt.
Yes.
Here we know that the number of clusters will always is 3.
Yeah.
Suppose we don't know the number of clusters, then can we do any?
Very good question. Very good question. So keep this question. We'll discuss it little later. Keep this question. Ask this question at the end of this discussion. We will dwell on that.
Okay.
So this question is this step is clear that now you got these 3 random mu. Now re-estimate the clusters for each xi, the cluster index for each xi. Let us do that. So what you will get? Your cluster will be formed something like all the points which are closer to blue will be in blue cluster, right? And this is your red cluster, probably something like this. Green cluster is something like this. Right? Now what you do is, now next step is re-estimate mu c. Basically, given given ci for each xi, re-estimate mu c for each c. Is that clear? Let us do that. Now, where will be the new centroid? Where will the new centroid be now? This centroid will move to the center, right? It will be somewhere here, right? The red one will be somewhere here. Green one will be somewhere here. Now you find the, now next step is go back to step 2. Until convergence. I will discuss what is convergence. This is an iterative algorithm. So go to step 2 until convergence. So what you will find now, see these points, they are closer to red than to blue. So your red becomes like this. Green is still like this. Right? Now, next step again, step 3, given ci for each xi, again re-estimate the centroids. What you get now? Okay, so you see the blue point, sorry, the blue point, we didn't draw. It will move a little bit towards this side, right? Because there are now less points here. So it will be somewhere here. Red will be somewhere in the middle, right? Because these points will pull the red one here. And the green will be somewhere here only. Now again, step 2, right here, go back to step 2. What you find is almost like this. Red one is, means there will be bisector here, right? Sorry, it should have been red color. So the bisector will be somewhere in the middle, right? All these points belong to red. And similarly here, all these points belong to red. And these are all blue. Now what you get? Further, this will move a little bit here, red will move a little bit here. Ultimately, it will converge that red will take up this cluster, blue will take up this cluster. And the convergence will be achieved when the mu's will not move any further, right? See now the mu's are moving so large with large distances, but after some time the mu's will stop changing, right? Which means here the mu c is almost constant. For all c. Mu c are almost constant. Then you can say it is converged, right? And you will ultimately find that you will achieve this kind of state, means green, red, and blue. Is this clear? K-means clustering.
Yes, sir.
Okay. Anybody has any questions at this point?
No, sir. Someone has asked a question. I have same doubt. How can we say that there are only 3 clusters here? It might
Okay.
be 4, might be 2.
Good point. Good point. I will just open the chat window. Okay. How do you know there are only 3 clusters? Okay. So now this number of clusters is a hyperparameter. Is a hyperparameter. What does it mean? It means that we are not optimizing it directly in this iterative EM algorithm, but rather we are either using some intelligence to give this number, or we are we can also monitor. For example, if I just use 2 clusters, 2 values, then I will see the data is not very well represented because for any reason, maybe my output is not very good. So generally there has to be some other measure. For example, you do visual inspection, or these clusters are used for the next task and that task is not performing very well, then you kind of re-examine your number of hyperparameters in clustering, that let me change this hyperparameter and see if the next task performs better, right? So we have to use some other mechanism to tune this hyperparameter, and that mechanism depends on, it varies from application to application. If my application is just, okay, I can do a visual inspection, that is all right. Otherwise, these clusters are used for some next task, then the accuracy of that task can help me tune this hyperparameter, right? Is that
Sir,
clear?
sir, can we use convergence as a metric to decide the number of clusters?
How can you?
As in the distance from centroid to each point in that cluster should be some threshold.
Yeah, if that is useful for your task, if you want to make clusters with minimum spread, then yes, that can be one criterion to choose your hyperparameter. Yes. So this is called unsupervised clustering. Why unsupervised? Because you only had the data to start with, and you didn't have any target labels or any desired labels, right? You just had some data to start with. This is unsupervised. Supervised means when I give you the pairs, like X, like if you remember for speech recognition or classification, if I tell you, okay, this data belongs to this class, this data belongs to this class, that is supervised uh, machine learning. But this is unsupervised because I just give you raw data, just the points, and you do whatever you want to do with it. And if you're clustering, then you cluster it the way you want. Okay. Any questions in K-means clustering? Now go through these slides. There is, everything is kind of told in a mathematical way, like the same Euclidean distance. We call it a distortion measure. Basically, distortion measure is sum of all the Euclidean distances, like distance of this point from centroid, this point from centroid, this point from this centroid, this point from this centroid. So all that distance, if you sum them up and you want to minimize that, as Jayant told, so I may minimize the maximum distance or I may minimize the overall distance. So this is distortion measure we define, and then K is the cluster index. We had C, this is K. We used I, here it is used N. So just notation is different, everything else is same. And that's it. And then there is some optimization formula. We just derived these, we just intuitively try to understand the meaning of these equations. But this is the EM algorithm, expectation maximization algorithm, where you do two steps. One, you try to get the centroids. Next, you try to get all the points which belong to that centroid and do it iteratively. Okay. Now we come to limitations of this method. This method has a limitation. The limitation is that in this case, all the data points were almost similar in their spread. Their standard deviation or variance about the mean is almost similar, right? What if we have very unsimilar or very uneven spread? For example, we are discussing here limitations of k-means. So one limitation is if variance of each cluster is or has a lot of variability. So basically you have one cluster which is very small, one cluster which is very big. Right? So even if you get perfect centroids, even if you start with perfect centroids here and here, still if you draw a perpendicular bisector here somewhere, these points will belong to green. So your clusters will be something like this. These all are green points. These all are red points. So you cannot get a perfect kind of clustering, right? And also another limitation could be if I give you a point X, what is the probability of cluster given Xi? What is the probability that Ci is green given Xi? So now you see these points belong to the margin of centroid, right? These points belong to margin of this centroid, whereas these points are well inside the centroid or well inside the cluster. So if I want to estimate the probability of this distribution, the probability distribution, then I cannot get from k-means clustering. K-means clustering does a hard clustering, not a soft clustering. Right? Are you getting this point? That I know that these points belong to the margin, so they are very less. We are very less confident that they actually belong to the green cluster or the red cluster. They are on the margin. So, but this we need to get an approach which also tells us what is the probability that actually this Ci belongs to. Okay, that this particular Xi has this label, probability of the label given the data point. So ideally, if I look at this point here, this probability should be very small, 0.1 probably. And here, if you see, this should be very large, almost close to 1. Right? Okay. So to get these advantages, we come to Gaussian mixture model. It is also an unsupervised approach, but instead of modeling these points just with a centroid, we model it with a centroid and a variance term. So Gaussian mixture model, let's say you have, even if you have imbalanced data like this, it will say, okay, let us model it with this Gaussian. So what you get here is it has a mean and it has a variance. There is some variance. Similarly, the red one, it has got a mean mu and some variance sigma. Right? So how many parameters are there? Can anybody tell? How many parameters are there?
4.
Think carefully and tell me how many numbers.
6 each.
6 turns.
12. 12.
Okay. Let us see. So each mu will have 2 parameters, right? Into 2. There are 2 of these, right? Each sigma has how many?
4.
4 into 2 of these. So total, how many you get?
12.
4 plus 8, 12. Very good. Yeah, 12 is the answer. So see, earlier you had only 4. If you would have used k-means clustering, you would have had only 4 parameters. But now, since you're also keeping track of the variance term, you have 12 parameters. So number of parameters has increased, but your modeling efficiency and the advantages, like you can probability of each point, probability of the cluster for a given point, that has also increased, right? So now I can model it. This is one Gaussian. All of you are familiar with Gaussian distribution?
Yes.
This is Gaussian distribution. P of x given mu comma sigma. What is this?
1 by under root 2 pi determinant of sigma exponential
Is it 1 upon 2 or d upon 2?
1 by 2.
Okay. Exponential.
No, whole term will have d by 2.
Pardon?
The whole term 1 upon under root 2 pi determinant of sigma will have a d by 2 term.
Like this?
And also root 2 pi.
This is there. Okay, then exponential of minus 1 upon 2, x minus mu. Yes? Yes? Somebody?
Transpose
Transpose,
First,
sigma inverse.
mu.
x minus
Right? So this is what we get. This is called the Gaussian distribution. But now what is happening here is we have multiple Gaussians. We need 2 Gaussians, not just single Gaussian. So what we do, I will say probability of x. I can say this is equal to probability of some cluster C, comma x. Is this formula correct? I'm just introducing a latent variable C and then marginalizing over that latent variable so that ultimately it is P of x only, right? No problem. Now I can say this is P of C times P of x given C. C is my cluster index. If I know C, I know this is a Gaussian distribution. So you can also call it as, okay. Instead of P, you can call it as N, right? Because it's normal distribution. That is conventionally used. So this will be normal X given mu for the particular C, sigma for the particular C. Right? You know this. Now what is this? What is this distribution? P of C. C can be 1 or 2. What is this distribution?
Prior probability.
Pardon?
Prior knowledge, a priori probability.
Prior or some prior knowledge. Yeah, but what is this distribution? It's called a categorical distribution. Categorical distribution. What does that mean? It means C can take two values. So probability of C equal to 1 will have some number A. Probability of C equal to 2 will have some number A2. Okay, A1. Or people generally use W's here, W1, W2. Some people also, I think Bishop's book uses pi, some number pi, pi1, pi2. I think they use pi or W. I don't remember exactly. Yeah. So what is this distribution? Okay. How many parameters are there in Gaussian distribution in each Gaussian distribution? How many parameters are there?
6.
Take single Gaussian first. 6. Okay.
Yes, 6.
Yeah. Correct. 6. You are right. So this has got number of parameters. This has got 2 and this has got 4, right? And how many parameters this distribution has got? This whole thing into 2, right? Total we have got 12 parameters in the two Gaussians. Now in the categorical distribution, how many parameters are there?
C minus 1 means number of classes minus
Yeah, there are two classes.
1.
Yes, very good. And which one is that? Because pi2 is simply 1 minus pi1. Right? Because their sum should be 1. Right? So we have got only single parameter. So total number of parameters becomes how many? 13 parameters. So here you can say plus 1. Total is 13. This is for weights. I see. Okay. Is that clear? This is a Gaussian mixture model. This is a Gaussian mixture model. You first get a class with some random probability, means with this particular weight, and then you, given that class, you get the point. So this is the idea of Gaussian mixture model. So ultimately you are just modeling probability of X, right?
Sorry, sir.
Given the cluster index. So you say probability of X given the cluster is a Gaussian and we have multiple Gaussians available. So you introduce a latent variable called C, and in this way you represent your distribution. Yeah, please ask questions.
Sir, the formula of Gaussian distribution is, I think, not right.
Okay.
D should be the on 2 pi.
Pardon? D should be on 2 pi.
Yes, sir. D should be the 2 pi power. Yes, sir. Yes, sir. And here should be a 1 by 2 only. At sigma. Sigma power only 1 by 2.
Okay.
Yes.
Thank you. Thank you. This is to the power d, and this is yeah. I think this is correct. Thank you. Thank you very much. So this is what is Gaussian mixture model. Anybody has any questions here? So things to remember is that this is an unsupervised model. You just have data and you are clustering the data and assuming each, this is a cluster, and the advantage which it gives is advantage, very important, which is very important for speech recognition also. Advantage. The advantage is that given an unknown point x, right, I can estimate what is the probability of x, right? For example, if you get an x which is very far here, and I ask you, what is the probability of this x? Then you will say, oh, this is very remote. It has a very low probability, right? Very, very low probability. But if I give you an x from here, you will say, yeah, this has got a significant probability to occur. Like if I ask you the sound if you build a Gaussian mixture model for all kinds of sounds, like you extract some, let's say formants or MFCC features just for the sound, and you create a Gaussian mixture model, and then only for sounds. So you create sorry, create a GMM for a sound, create another GMM for E sound, and this will give you probability of x, right, from a GMM, or I can say GMM underscore and this will give you a probability of x from GMM of E, right? And then whichever has higher value, you can simply choose that, oh, this sound is a sound or this sound is E sound, right? So in this way, a GMM can be used for classification. Thus, we can use GMM for classification. Okay, but in this case, this part is supervised. This part is supervised because you were given all the x which belong to a sound, and you were also given all the x which belong to the E sound. Then within this data set of all the sounds, you did an unsupervised modeling, unsupervised clustering using GMMs. And similarly, within the E sounds, you did an unsupervised clustering using GMMs. But overall, the approach is supervised at the level of phonemes. It is not supervised at the level of clusters, but supervised at the level of phonemes, right? Supervised at the level of phonemes. but unsupervised at the level of clusters. So that's how you use GMMs for speech recognition. Is this clear? Anybody has any questions? Or else we can stop here.
Sir, is PCs directly given or any parameter is given so that we can write PC, categorical distribution?
This one?
Yes, sir. Yes, sir.
Okay.
Because if PC is not given directly, then it will give mean and variance. Then there should be two parameter here.
Yes, very good question. Very good question. Now, we did not discuss how to estimate mu c, sigma c, pc, or pi c. All these things we did not discuss. For this, I would say you go through the lecture. How do you estimate these values? So this will be available in the lectures, in the recordings. I will upload the recordings on our YouTube channel playlist, and you can learn it from there. It's very simple. Just go through it, and also since you have already done GMMs before, so I don't think it should be difficult, right? You already studied the theory before.